All right, so let's get started. So today we'll finish the process and interrupt parts. Actually, there's just very few about the interrupts, how does it work? And after that, we'll talk about the memory management. Okay, but before that, I think let's go through some Q&A. And actually, there are a lot of Q&A, so I'm not able to go through all of the Q&A, so I just pick several. I think it is more representative ones. And like if your questions like does not be answered on this list, and if you already want some answers about your question, you can come to me after the class. So the first one is about thread. So the definition is here. Actually, it's just like executes within the same program in a shared memory address space, and usually open files, patch tables, those kind of things that are shared between threads within the same process. So last time people are asking about, because in Linux there is a function called clone, and clone is very similar to the fork function. And the difference is like actually clone can control about which kind of resource can be shared between threads. So actually like this clone-vm is about those threads can share the memory address, and fs is kind of the like file system and files, and then some signal like these kind of things. So actually those kind of parameters in this clone function means what kind of resource you are going to share between process. Okay, so there is one interesting thing is about in Linux, actually we say the threads that they share the resource, they're not using the copy on write because they really share the resource. I mean, they really share the patch table. So even there is some thread modifies the patch table, all the threads can see this change. Okay, so copy on write is for the process because process has their own independent resource. So when one process is going to fork another process, actually they will do copy on write to avoid time-consuming data copy. But thread, actually, they are all shared and they're not using copy on write. So even one thread modifies some shared resource, there is no copy on write there. Okay. So also there are some question about like in Linux, actually, you cannot really see thread or process in the, for example, in the Linux source code. And the reason is because Linux coded a task. Because if you still remember, like at the very beginning, we say like in Linux, we call the PCB as the task dash structure, right? So text dash structure is going to describe the process and thread. So Linux code a task and it refers to both process and threads. And the difference between process and thread, I mean, in terms of the task, is about how much of resource they are shared between this kind of instance. So process have their own address space, but threads within a process will share the same address space. Okay, so they are all called tasks, but the difference just about how much of the resource they can share. And the second question is about the CPU mode switching. So like before switching to kernel mode, CPU will automatically set essential register on the kernel stack, because people are asking about, hey, when we are going to switch from the user mode to kernel mode, and how about those kind of user related kind of register, those kind of things. And actually those kind of things will be stored on the kernel stack. So each process has their own kernel stack, and usually the size of the kernel stack is around 2 to the 3 of the patch size. So you can think about each process, they will have the kind of 8 kilobyte to 12 kilobyte of the space they're allocated for kernel stack. So when they're going to do the when they're going to do the mode switching, then those kind of user related register will be stored at those area. Okay. So the goal of CFS. So actually, like we talk about the goal is fairness and better interactive. And last time I said not real time. I mean like not how real time, because CFS cannot provide how real time. How real time means like for each process, if they are how real time, they will have a deadline, like they should finish in what kind of a time. It is how real time. So there is no room to be delayed. But CFS can approach soft real time. I mean, if there is a little bit delay for some process execution, actually CFS can do these kind of things. Okay. Oh, and there's another thing is about the reason like CFS cannot approach how real time is because if we're going to meet the hard real-time requirement, usually it means to let some high priority process occupy CPU aggressively. So when one process can get a full kind of load of the CPU, it means like it's possible it can meet their hard real-time requirement. But actually, for some other process, if they are not like high priority process, they cannot get any CPU. So actually, there is some contradiction between the hard real-time and then you're going to make it fair. And the last one, I think it is quite, I would say, like interesting, but I mean, this part will not be, I mean, on your exam. I just want to share some kind of information with you. Like people are asking about software and hardware context switch. So actually, software context switch is the things you learned last week. Just like you, I mean, when there is a process, they are going to be rescheduled, and operating system will do some like schedule MM and then schedule to function to switch the address space and switch a process. And those are called software context switch because most of the flow, they are controlled by the operating system, and operating system is kind of software. So it is called software context switch. And actually, there's another thing called hardware context switch. So hardware context switch is like CPU's hardware mechanism, or like you can think about there are some circuit designs that can go through the context switch flow. But actually, it is not a context switch. They are run in the operating system base. I mean, there are some lightweight context switch that can be run inside the CPU. So there is an instance is about most of the CPU now they support hyperthreading code. Okay, so hyperthreading is just like there is one hardware code, but actually they can pretend as two software cores there. So when you open the Linux and then you type like TOP, the top instruction there, and actually if you press 1, you can see there are a lot of cores there, right? And the number of cores will be more than the hardware cores you have in your CPU. And the reason is because that top information that exposed to you is about including the hyperthreading part. Okay, so that's about too much, but like I'm going to let you know, like hyperthreading, they use a hardware context switch to switch between two hyperthreads. Okay, so but yeah, there are too much details here, so I just skip the hardware context switch for now. Okay, so actually there's another question is about the CFS, but I think that is super important. So let me do some clarifications on the past following few weeks when we talk about the CFS. So I think the main goal and the concept there are all the same, but today I'm going to use an example to let you understand how CFS works. So there's one thing that I'm going to do some modification here. So actually let me define two things. The first is about the allocated CPU time. So you can think about if there are n processes that are in the run queue, and then for all the process, the total time to run all the process, let's say is this kind of schedule period. Okay, so you can think about schedule period. If it is 6 milliseconds, then in this 6 milliseconds, we need to serve all the n process in the run queue. Okay, but the thing is like each process has different priority, right? So there is a calculation is like nice k weight is about if there are there are k here. You can think about there are k process in the run queue, then we sum up all the weights among those k process, and then this nice dash weight is about each process. What is the weight value of each process? So if you are confused about what is the weight here, so actually weight is just like this. So there is nice value from -20 to 19, right? So for each nice value, you can get a specific weight. So for example, -20, you can get like at 761, and for the nice value 19, you can get a weight value like 15. So these are weight values. So coming back. So after doing this calculation, actually it's just about to allocate the maximum CPU time for each process. Okay, and then I slightly modified this theory kind of formula because last time I forgot this clause. Actually, the V runtime will be add on to the prior virtual runtime. Okay, and most of the things actually they're the same. So let's just directly jump into the example. So one example is like if there are two processes the first process called process 1, second one called process 2, and process 1's nice value, let's assume to be 0, and then process 2 has like kind of nice value 19. And actually, we are going to first calculate the allocated CPU time first. So actually, P1 and P2, if overall they can have like 6 milliseconds, for example, then we can do like 6 millisecond times, because processor 1 nice value 0 is 24, like this. This is 0 here, so this is 1024, and 19 here is kind of 15. Okay, so 1024 over 1024 plus 15. So P1 at most it can run for 5.9 milliseconds of time. Okay. And on the other hand, like P2 should be like 6 milliseconds times 15 over 1024 plus 15. So it will be around 0.1 milliseconds. Okay. So according to their nice value, or like according to their priority, actually processor 1 will get more CPU resource because it has higher priority. Okay. So this is the like ideal case, or like you can think about the maximum CPU that can be allocated for each process. So let's start for running the 2 process. So at the very beginning, we will do the initialization. So each virtual runtime for each process, they will get 0. Okay, because this is the initialization. So all the virtual runtime, like no processes run before that, so they'll get 0. So P1 will run first usually because P1 is getting higher priority here. So if P1 after 1 millisecond, if P1 fetches the IO, then because fetching the IO, so we need to switch off P1, right? Because when there is an IO, so we need to do a process context switch. Okay, so after doing the process context switch, actually there's only 2 processes here, so we will switch in process 2. Okay, so after switching process 2, if there is an assumption is if after 0.05 millisecond, P1 finish the IO serving. I mean, for example, P1 get the data from the storage device now, and P1 is back to the run queue. Okay, so here comes the case. Should P2 keeps running, or like should we prioritize P1? So for CFS, we do this calculation. Actually, we need to calculate the virtual runtime. So the virtual runtime is here. So delta dash execution means how long does this process run? So you can see like for process 1, because it runs for 1 milliseconds. So here's 1 and times nice dash 0 dash wait. So dash 0 is about we need some kind of wall time, or like we need some baseline. So usually this calculation, like we will take the nice dash 0 dash wait, that is 1024 as our, I think it's kind of nominator place. And then for nice dash wait here is about the wait value for that process. Okay, so for example, for P1, for here, nice dash wait will be 1024, but for P2 here, nice dash wait will be 15 because the nice value for P2 is 19. So this wait value will be 15. Okay, so after doing some calculation, you will find like, hey, actually the P1's virtual runtime is only 1, and P2 actually it gets 3. Okay, so according to the CFS, these numbers will be updated to the red-black tree. So after the update, actually, we'll always pick the smaller one to reschedule. So 1 is smaller than 3. So P1 now can preempt P2. Okay. So actually P2 only run for 0.05 millisecond, and you will be preempted by P1. So P1 can come back to run to use up the rest of the CPU resource. Okay. So this is the example for the CFS. Okay. Okay. So that is for the CFS part. Then let's keep doing the recap part. So we talk about like process context switch, and we also define what is process context. Actually, you can think about it's just an environment to run a process. So it includes user address space, just like patch table, hardware register, just like the program counter, and then those kernel data structure, like kernel stacks, those kind of things. Okay. So we talk about like process context switch. Actually, that includes they include two kind of component. One is called switch-mm, and it is going to switch the virtual memory mapping. And then the other is switch-to function. It switch the process stats. So we talk about the details about like switch-mm, what kind of things that are included. So I will skip here. And we also talk about switch-2, but actually the main key concept is when you are going to do a process context switch, you need to switch the virtual memory mapping and then the process state. I think this is the core part that I'm going to let you know. Okay, so system call part. Actually, last time we quickly go through the system call, and then the idea behind system call is very similar to interrupt. So this is the reason we don't talk too much about system call. Okay, so system call, you can think about it is a way for application to signal or like to run the kernel service. Because when application they are running in the user space, they need some way to interact with kernel, right? And system call is one way. Okay. So how to signal the CPU to run the kernel? Actually, there's a thing called software interrupt. Okay. So software interrupt means if CPU run the instruction code int $0x80, it means CPU now needs to run the it is an interrupt instruction, and we need to run some system call service. Okay, so after running this instruction, actually CPU will from the user mode will be changed to the kernel mode, just like this. Processor A now is in the user mode, but at the time like the CPU run this instruction, CPU will dive into the kernel mode. Okay, and there is another parameter is what kind of system call that we are now we need to run. Actually, there is a system call number. So according to a number, for example, number 0, for example, maybe it is read, and maybe 1 is kind of write, for example, like this. So inside the system call table, there is a way for the CPU to know where is the source code for this kind of corresponding system call number. For example, system call number 0 means, for example, is a read operation, but we need to know what kind of things we need to do for this read operation, right? So we need to find where is the code of this for these read operations. And then we will check the system call table to get where is the code is, and CPU can run the code. Okay. After running the system call, actually CPU will get back to the user mode and then keep running on the user process. Okay. Okay. So we also talk about like that is software, and now there is hardware events here. So there are two hardware events for CPU to work with the store hardware device. So one is called porting and another is interrupt. Okay. So porting is the kernel will check hardware status periodically. So for example, for every like 1 millisecond, kernel will stop all the things and then to check, hey, if the IO is finished, like these kind of things. And interrupt on the other hand is that the hardware device to signal to the kernel. Okay, so let the hardware device send a message to the CPU to let the CPU know the hardware device is finished. Okay, so we talk about like what kind of things will cause, like how the interrupts be called, and hardware device will physically produce electronic signals to the CPU. Okay, so CPU can directly get the information, and then we also show you like the example, like hey, if there's a motherboard and then there is north bridge and south bridge, and usually like south bridge will be connected to several different kind of slower hardware device like keyboard, hard disk drive, and PCI SSD. Okay, so when we are going to do the interrupt, actually keyboard, hard disk drive, and PCI SSD will send a signal, an electronic signal to the CPU. So CPU can know it is now interrupted by what kind of device. Okay. Okay, so same as system call, actually interrupt, there are also according to their number. I mean, different interrupt number, different interrupt value, it means different interrupts. Okay, so there are 256 interrupts number usually. And like For example, for like IRQ0, it means like the timer interrupt, IRQ1, just like the keyboard interrupt. So different numbers means what kind of device and what kind of service it is going to do. Okay, so we also show you this last time. I think this is not quite, I think it's not quite like important, just that you know current systems, they are using this kind of mechanism to map the interrupt vector number and then interrupt request. Okay. Okay, so I think we stopped at a prior page, and today we are starting right here. So how an interrupt works. So we put back our example figure here. There is a motherboard and there are south bridge memory, CPU, and south bridge connects to several kind of device like timer, keyboard, those kind of things. And they are connected by the cable. So you can think like for timer, there's a cable to the interrupt controller, and it is called IRQ0 will be sent through this kind of cable. Okay. So let me give you an example. So if now you type something on a keyboard, actually keyboard will send a signal to CPU, and the signal will stand by this cable. Okay. So for example, because we know keyboard, the interrupt, sorry. So we know like the interrupt request for the keyboard is IRQ1, right? So inside the interrupt controller, actually, interrupt controller will help to translate the IRQ1 back to the interrupt vector number. So with this number, CPU is possible to know which interrupt it is now. Okay, so for example, IRQ1 will be mapped back to INT 0x81. Okay, so like this. So like this. This is 0 at 80, and this is master PIC, right? So keyboard is the second one. So you can think about the second one is like 81. Okay, so there is a mapping between this interrupt vector, this interrupt vector number and this interrupt request. Okay. So with this interrupt vector number, actually the interrupt vector number will be sent to the CPU's kind of like interrupt controller. You can think about like this. So the key thing is actually our goal is, so where is the program, where is the location of the program? Because we now know like there is a keyboard interrupt, but what kind of things will CPU do to interact with this keyboard interrupt? So actually there is a piece of code, right? There's a piece of code to define what should CPU do to interact with this keyboard. And where should the CPU get the piece of code? So CPU can get the piece of code by using this interrupt vector number. So like this. Actually, inside the memory, it will be striped into, or you can think about, it can be partitioned into several slots. So each slot, you can see there is a address. Actually, this is just an example. I mean, in the real system, you will not start from 0x0 usually. You will start from any other place, but I think it will not be 0x0. But this is just an example. So for example, like 0x81 now, we need to find where is 0x81. Okay, so actually for each slot, it is 4 bytes. And the reason for 4 bytes is because inside each slot, you need to store two kind of things. One is like code segment, another is an instruction pointer. So with using the code segment and instruction pointer, we can know what is the first instruction of the keyboard code. Okay. So 0x81 will be multiplied by 4 bytes. So now we can get 0x204. Okay. So CPU will fetch the data from 0x204, and inside the data, actually, there is a code segment and an instruction pointer. So with using this code segment and instruction pointer, actually, we can get where is the code for serving this keyboard interrupt. Okay, where is the beginning of the code is. So actually, like for example, CS plum, IP plum, maybe it points to this location, and CPU will come back to read this location. So after reading this location, actually, inside this location, there is a pointer to point to the starting point of this keyboard driver, like these kind of things. Okay, then CPU can run the keyboard driver. Okay, so like here is the code of ISR. Okay, and then CPU will keep executing like maybe ISR. Here is 82, 83, 84. Okay. So this is the way like how CPU handles this kind of interrupt service. So question. Okay. Yep. Okay. So there's a question is why not just directly get a code? But the point is, what is the size of the code? I mean, because different interrupts, they have different size of the code, right? For example, keyboard interrupt, maybe it is about 200 line of code. But maybe rewrite operation, there's 1,000 line of code. So you cannot really know where to get the code is. So you need some interaction to get the first instruction of that code. So you can start to execute it. Yeah. The reason is like, if there is, I mean, if the interrupt code there have different sizes, then you cannot really know where is the starting point for each interrupt, because it depends on how the operating system and the BIOS, how they decide where to put those code on. So we need some interactions to point to the beginning of the code. Yeah. Yep. Okay, so let's move on. Okay, so actually, the code of interrupt service routine, each interrupt service routine you can think about is kind of a piece of code to serve each interrupt. For example, ISR maybe like ISR 0 is for like read operation, and ISR 81 is the code to serve the keyboard. Okay, so this is about ISR. Okay, so interrupt service routine or interrupt handler is the function the kernel runs in response to a specific interrupt. So usually ISR is part of the device driver, like inside the kernel code. And here comes a challenge. Usually when the CPU is running the interrupt service routine, it is non-blockable. So non-blockable means that it cannot sleep. Because if it sleeps, then the CPU cannot get back to the original user process. So CPU will stop there. So CPU should finish ISR and then return back to the original process to keep the progress. So the thing is, but if this like interrupt service routine is a super long code, or like it needs to do a lot of things, then the system will block there to wait for the finish of the ISR, right? So for example, if now you have a kind of network card and you are going to get the data from the network card, but actually maybe you only need the very few, maybe 2 or 3 bytes for the network card, but actually the overall size of the network package is like several megabyte there. Then you need to wait for several megabyte to finish, and then you need to wait for CPU to process on the several megabyte, and you can do another things. So in this case, Linux kernel splits the ISR into 2 parts. It is top halves and bottom halves. So top halves means to run immediately upon receipt of the interrupt and performs only the work that is time critical. So you can think about, because the interrupt service routine is super huge, so maybe there are several things that we must run at this moment, and they will be split into top halves. But the rest of it is not that time critical. We can postpone, we can delay it. So just like this kind of bottom halves part. So for bottom halves, work that can be performed later is deferred until the bottom half. Okay. So here's an example. There is a network card receive a packet. So for top halves, it moves the packet from the buffer in the network card to host memory, because usually the data package will first be moved on the network card, right? From the other network card. Okay. But if you don't move the data from the network card to the whole systems, then this network card cannot serve for other requests. So we need to move it from the network card to the host system first. So then other requests can be sent to the network card later. Okay. And bottom half is like what are you are going to process on those packets. For example, you need to decode a packet, right? You need to decide what kind of things you are going to do on a packet. But this is not like time critical because you will not block any later device. It only depends on the process you are going to do on this packet. So it is possible to delay these kind of things until the next time that process is going to process the packet, then we can resume it. Okay, so this is about the bottom halves. Okay. Okay, so that is about the process and interrupt. So then we'll move on to the memory management part. Okay, so here are the agenda that we will cover for the memory management. Actually, it will be mainly split into two parts, the physical memory management and the virtual memory management. And if I remember correctly, for the undergraduate operating system, we do not really talk too much about the physical memory part. Most of the time we talk about the virtual memory. So I put some things maybe it is good to you to know for the physical memory here. So I will talk about the physical memory first, and then following on we'll talk about the virtual memory part. So if we still have sometimes we can talk about some research topics that relate to this kind of process and memory management. Okay. So at the very beginning of the same things, we need to talk about some basic concepts of memory management. So there are two things for memory management. One is called patch frame and another is called patch. So patch frame is the CPU will partition physical address space to chunks with the same size. And a patch, it means CPU will partition virtual address space to chunks with the same size. So the difference is the address space. There are physical address space and there are virtual address space. But I think it is not easy to understand what's the meaning for virtual and physical. So physical, you can think about the location where the data stored on the device. So because now we usually use DRAM, right? So if we have a 4 GB DRAM, then how to partition the DRAM? How to know where the data is stored on which place? Okay, so the address on DRAM you can think about is a physical. But virtual, it means the location where the programmers think the data is. So it doesn't relate to what kind of device it is, because programmer doesn't really know what is the address on DRAM. Not even DRAM. I mean, for example, like currently we have swap, right? The same things like programmer doesn't really know the program is now on the DRAM or on the storage device because we haven't swapping. So it is possible maybe the data now is on DRAM and later on it is on the swap device, but programmer doesn't know. So for the virtual, actually, it's just about what does programmer thinks. Okay, so we'll have more details about the virtual probably next week. And this week we'll first talk about the physical things. So there are more kind of details about the basic part. So like this, actually, if this is a DRAM, okay. So if this is a DRAM, and then if we are going to do the partition, you can think about like this. So the whole DRAM is just a linear space, like if it is the 4 GB, and then we will divide by a lot of 4 KB patch frame, for example, like this. Okay, so normally people are using 4 KB now, but I mean, it depends. I mean, it is possible to use larger if you are going to use it. Okay, so the thing is, but this should be in the same size. Like this is 4 KB and all of them should be in the 4 KB. Otherwise, there are some fragmentation issues there. And we will talk about the fragmentation later. Okay. So actually, like, if this is a DRAM, actually there are some places they will be allocated for the kernel, and there are some places they will allocated for the user process. Okay, and we will talk about this later. Okay, so let me give you a quick example, like, because when we are writing a C program, there is we frequently will call the memory allocation function, right? The MALOC function to get the memory address. So if P1 calls MLOC functions, the memory allocation function, then the kernel allocates patch frame, for example, like this, the allocated one, and then kernel will update the patch tables, okay? And then CPU running P1 will work the patch table to get where is the location of the allocated patch frame, okay? So this is the simple example, like how is the connection between the memory allocation and then to all the patch table things, okay? So actually this example, you can also think about, last time we talked about there is a mailing address and then there is a like the absolute address layer. It is the same things, you can just use the same example, put it here, okay? So kernel manage all patch frames and maintains patch table. So there are several things we need to know. First about how to manage each patch frame. And then the second one is how to do the allocation. So what do I mean for how to manage each patch frame is, I mean, in the Linux, how can Linux have a data structure to manage those patch frame? What is the data structure and what kind of information will be inside that data structure? And how to do the allocation, you can think about like this. If this is a large space and if there are several processes there, then there are some processes they will allocate and there are some processes they will return their space to the operating system, right? So how to do a good allocation? You guys maybe learn about like fast speed, burst speed, and warp speed, right? But how about Linux? What kind of allocation does Linux pick for this kind of allocation? Okay. Okay. Oh, so that is for the physical part. Actually, there is another side is for the virtual memory management part. So for virtual memory management, just like it let all processes share the same physical address space via patch table, right? Because come to think about, if you in your computer you just have one DRAM device, for example, one DRAM is kind of 4 GB, and you only have one DRAM inside. Then, but you have 10 processes they are running simultaneously, and actually those 10 processes they use the same DRAM, right? Usually you will not say one process you can get only 400 megabytes for that process, right? So all the process will share the DRAM resource. So in this case, how to manage these kind of things? Because some process maybe it is like memory bound or like memory hungry, so it needs more memory, it needs more patch frames. But maybe there are some processes that are CPU bound. I mean, they only need very few patch frames. So how to do this kind of dynamically management? And those are about the virtual memory management. So here are some kind of thing is a basic knowledge that you need to know for the hardware part. So actually inside CPU, there are two hardware components. One is called TLB. I think it's kind of translation local site buffer, and the other is MMU. So when CPU is going to get the data from memory, actually CPU needs to know the physical address of the memory, right? But actually, currently, when the CPU get the instruction from the code, they're all virtual address, because programmer only know the virtual address, same as compiler. Compiler only know the virtual address, right? And now if we are going to get the physical address, we need a translation between them. So CPU will first check the TLB. So TLB, you can think about it's just like a very small cache. Inside the cache, the cache content is the translation result for each virtual address. Okay, so you can think about TLB inside. There are a lot of this virtual address is translated to that physical address. Okay, but actually there are too many of these kind of entries. So TLB probably will not be able to hold all these kind of translation results. So you can think about maybe there is only 1% of the translation result that can be stored in the TLB. Okay, so first of all, CPU will check the TLB. If CPU cannot find the virtual address in the TLB, so CPU needs to do it by itself. But if CPU can find the TLB entry, I mean, the virtual address is inside the TLB, CPU can directly get a physical address. CPU doesn't need to do any further things to get the physical address. So with this physical address, CPU can directly access the memory. Okay, so if the virtual address is not in the TLB, CPU needs to do the patch table working, and then CPU will send this will move this virtual address to the MMU. So it is called memory management unit. So actually MMU is not a very complex component. You can think about MMU, most of the things MMU do is to do the offset and then to add some integer to another integer. They're just very simple operation there. Okay, so what I mean for simple operation is actually MMU, we're going to go through the patch table. And the reason to go through a patch table is current Linux, they are using the 4-level patch tables. Okay, so I mean, in the undergraduate textbook, there are a lot of different kind of paging. I mean, there's kind of only one patch table paging. There are also several multi-level paging, those kind of things. But in Linux, they are using the 4-level paging. Okay, and we'll have go into the details. I think it's next week. I'll tell you like how MMU do this kind of 4-level patching things. Okay. So after doing this kind of 4-level patch table translation, actually MMU can get a physical address. Okay, and using this physical address, CPU can get the patch data. Okay, and then because the virtual address is translated to the physical address by the MMU, so usually MMU will store this translation resource into the TOB. So next time if there is the same virtual address inside the CPUs, the TOB, I mean the CPU can find the result in a TOB. Okay, so there is a very important thing. Because inside the CPU, they will run different kind of process, right? So the things I'm now talking now, they're just only for one process. So each process, they will have their own patch table, right? So because they have their own patch table, so inside the TOB, they will only store for that process. So now when you are going to switch to another process, it means the TOB cannot be used for the next process, right? Because the TOB store the translation result, and the translation result is related to the patch table. But the patch table can only be used by the process that are running now. So when we are going to do the context switch, we need to switch the TOB, we need to switch the patch table. This is the reason. Okay. So, question? All right. So, okay. So let's move on to how to manage patch frame. So I think this week we only focus on the physical part. Maybe next week we will talk about virtual. Okay. So actually, if you learn like if you take the computer architecture course, maybe you will know there is a key phrase called byte addressable. Byte addressable means like current memory they're using the byte. I mean the smallest granularity to do the addressing is the byte. Okay, but actually in the operating system or like in most of the system now, like there is a things called patch, and patch is 4 kilobytes. So actually 4 kilobytes is larger than 1 byte, right? So actually we need some management to manage these kind of things because byte addressable in only for the physical part. I mean the physical address part inside the device. But for CPU, usually we will look at this kind of things as a patch. Okay. So if we are going to manage this patch, we need some data structure. So inside of Linux, there is a data structure called structure patch. Okay, so this patch, usually there are more kind of fields, but I only get some, I think it is quite important things here. So for the flex part, you can think about they are talking about status. For example, if this is the dirty patch frame or like it is a locked patch frame or not. So dirty usually means like the patch frame is, that means the data inside the patch frame, they are updated. Okay, so the reason like it is called dirty is because for DRAM, usually the data will be moved from the secondary storage, like the hard disk drive or SSD to the DRAM, right? And the reason is DRAM is volatile. So volatile means that if you shut down your computer, all of the information, all of the data inside DRAM, they will volatile. Okay, they will not be there. Okay, so if the patch frame is dirty, it means when you are going to shut down your, for example, computer, you need to write back this kind of data to the non-volatile device, like hard disk drive or solid state drive. So you can make sure the data, they are all in the latest version. Okay, so this is why there is a dirty bit there. Okay, and also there are some other things like if the patch frame is locked or not. And then the second one is dash count. So simply just how many reference there are. So I mean like how many like process or like how many threads they are using this patch frame. So this one is highly related to the fork function. So if you still remember, when we are doing the fork, we will do copy on write, right? Because we don't want to copy out the patch frames at the same time we call the fork, because it will take too much of time. So we say at the time we call the fork, we will do copy on write. We only do the copy when the data is updated. So the same things, when you do the copy on write, the dash count counter will increase by 1. It means there are two processes, or like there are more processes they share this patch frame. Okay, so when the patch frame is kind of updated by the child process or the parent process, we will copy out, we will do a private copy. So at that time, the dash count will -1. It means that process get their own copy. Okay. So actually, there are some other things that we did not talk about early, but I think maybe later on, if you are interested in, maybe you can get some information from the networks. Like there's a concept is called patch cache. So patch cache is usually for file. What do I mean for file? You can think about in a storage device, maybe you will store a lot of like movie or music files, right? But when you are going to like play the music or like play the movie, actually the data should be moved from the memory, to be moved from the storage to the memory. Okay. But do you think about like, have you ever think about like if there are not enough space for the memory, we need to pick some very frequently used data in the memory, right? So that is for patch cache. So the file that are cached in the file, so the file that are cached in the memory, they are called patch cache. And usually if you only have 1 GB of like memory and you are going to open up a lot of files there, then the system can only cache few of them. So those patch frames, they are related to the storage device, related to the file. There is this kind of patch cache structure there. So we can use the patch cache structure to find out where the data is. Okay. So because there is a patch cache, so there is a question is about, I mean, the file is usually larger than 4 KB, just like movie is several gigabytes. So one movie will be partitioned into a lot of, I would say like kind of million of patch frames there. Okay, so which patch frames is for which data? So there is an index in there. Okay, and then like there are some kind of information for the patch replacement policy, because like there is a LRU head here just to maintain if the memory is not enough, we're going to throw away some patch frames, like these kind of things. What kind of we're going to throw away some data, then what kind of decision that we are going to make that is about patch replacement. And then there are also a virtual address, just like the patch virtual address here, to know where is the like virtual address is. Okay. So actually, this structure patch is quite huge. And then, for example, if there is kind of 40 bytes for each structure page, so you can just count, for example, this flex, maybe it is a unsigned long, so maybe it is a like 4 byte, for example, and this is 2 byte, this 2 byte like this, and you sum up all this kind of information, you can get each structure patch is like 40 byte. Okay, but like each structure patch can represent one patch frame. So for the 4 GB DRAM, actually we require like 40 megabyte of the information just for this data structure. We need 40 megabyte there. So yeah, I think this is not that huge, but it still takes some kind of overhead here just to maintain the information for each patch frame. Okay, so some basic concept of memory allocation. So initially, all memory is available. What I mean, all memory is like all the patch frames, they are available for user process. And you can think about like, because it is not used, so it is considered one large block of available memory. Or like in our textbook in the operating system concept, it is called a whole. So when a process needs memory, the system searches the set of a whole that is large enough for this process. So there is a thing called first fit, is to search and allocate the first hole that is big enough. Okay. But the thing is, like, this is just big enough for example, if now you need a 4 megabyte, but the first hole is like 4 gigabyte, the system will still return the 4 gigabyte to you, even like this is a very wasteful decision, but this is first fit. So you get the hole larger than you want. And best fit is to search all holes and allocate the smallest hole, which is big enough. And the overhead is time, because you need to search all the holes to get the best fit. Okay. And then the worst fit is to search all holes and allocate the largest one. It wastes both size and time. Maybe you are thinking about, and why do we need worst fit, right? So the reason I say waste size and time, especially for size, is at this moment it is a waste for size. But because our system is running, so no one knows the future. So for example, for the worst fit, for example, if the process now they are asking for like a smaller like memory space, for example, 1 megabyte, but if the system give it like 10 megabyte, it does a waste now because we waste for a 9 megabyte. But maybe several moments later, maybe this process used up to 10 megabyte. Then in this case, if you use the worst fit to allocate that 10 megabyte before, then you don't need to reallocate the new space for that process. So in the future, maybe it is a good, maybe the worst fit will become the best fit, maybe in the future. So it is hard to say. Okay. So, yep, I think let's take a 10 and come back later.